The concept of strain rate and the different methods used to control it can be difficult to understand. In this video, we will try to clarify this concept and discuss how it applies to your testing. Let's begin by defining strain. Strain is defined as the extension of a material when subjected to a force. We calculate strain by taking the material's change in length and dividing it by its original length. Now let's define strain rate. It is strain per unit of time. How do we display strain rate? This animation shows an example of a typical test run in strain control. The two dotted lines serve as the 20% upper and lower limits of the desired strain rate dictated by testing standards such as ISO 6892-1 or ASTM E8. Why is strain rate important? The material properties of some metallic materials are dependent on the rate at which they are tested. For example, even when testing the same material on identical systems, different test speeds can cause different results. Now let's take two samples of the same grade of material and test them on two different machines running at the same crosshead speed. If we were to plot the stress-strain curve from the two different systems, you would start to notice a difference in results. On this system, the yield strength is 300 megapascal, whereas on this system, the yield strength could be up to 10% higher. This is because the machine compliance, or stiffness, has an effect on the strain rate of the test. Machine compliance is when force is absorbed into the testing machine itself before the specimen begins to be affected. Machine compliance can differ depending on the stiffness of the test frame, the strength of the load cell, and other variables such as the type of grips and accessories being used. When testing on two different machines, this can result in different strain rate values despite apparently identical test conditions. So how do you ensure strain rate consistency in your testing? Most metals testing standards prescribe two methods to achieve this. One maintains a constant machine crosshead speed, while the other maintains a constant strain rate during the test. First, we will start with the simplest method, constant crosshead speed. In order to determine crosshead speed when using this method, common standards direct us to multiply the desired strain rate by the parallel length of the specimen. However, the machine speed calculated by this method may not produce the correct strain rate within the tolerances of your testing standard. This is because the machine compliance will reduce the strain rate of your test. In this case, you may need to run multiple tests in order to tune the correct machine speed before you can produce valid results. To summarize, the constant crosshead speed method is a very simple control method available on nearly any testing machine, and if done properly, still ensures repeatable and comparable results. The downside to using this method is that it is time-consuming because it requires the test to be run at a slow speed for a long period of time. It can also require multiple trial and error adjustments to the crosshead speed to ensure that your strain rate is in compliance with the testing standards. Now let's look at an example of a test using closed-loop strain control, where instead of maintaining a constant crosshead speed, the machine maintains a constant strain rate. In order to maintain a constant strain rate, the testing machine needs to speed up dramatically at the beginning of a test. This is to compensate for machine compliance as the force is increasing on the specimen. Once the specimen begins to yield, there will be little to no increase in force, as the stiffness of the specimen reduces significantly. In order to comply with the standards, the machine has to respond quickly and slow down at yield in order to prevent any overshoot in strain rate. Not every machine can successfully perform a test using constant strain rate, as it requires a responsive controller and a precise and stable drive system in order to maintain the tolerances required by the testing standard. Some machines are advertised as being able to achieve this method, but require the user to manually tune the gain settings of the controller, which can be difficult for even the most experienced system operator. It is vital that the gripping technique provides sufficient clamping force and minimal compliance, with jaw faces in good condition. The extensometer needs to be securely attached to the specimen, with knife edges in good condition. It must also be appropriate for the expected travel distance to minimize the effects of vibration and have a suitable ratio of parallel length to gauge length. It is important that the testing machine and extensometer be isolated from any sudden or repetitive vibrations or shocks, as this could cause interference with your testing. Why would you want to use closed-loop strain control? To ensure that you always have repeatable and comparable results, while complying with the international testing standards requirements. Because the machine speeds up during the elastic region of the test, testing times can be reduced by 35%, greatly increasing the throughput and efficiency of your lab. Using closed-loop strain control with Instron's advanced automatic gain algorithms means that minimal operator setup is required, and no specimens need to be sacrificed in order to tune the test. To learn more about strain control solutions for your lab, contact your Instron representative.